Good morning, everyone. This is Sachin Fiske from Electrical Engineering Department, SND College of Engineering and Research Center. In the previous section, we discussed some point related to PID or what is PID controller, P controller, integrated controller, or derivative controller. Now, here we are going to start the PID controller or the design of PID controller using root locus method. See, exactly, I'm repeating this PID controller in very short, or it is the repetition. The system that feeds the error forward to the plant or actual system are called as proportional control system. And the systems that feeds the integral of the error to the plant are called as integral control system. So the system that feeds the derivative of the control to the plant are called as a derivative control system. This PID stands for proportional plus integral plus derivative. That is proportional integral derivative. This combination of PD controller and PI controller gives us the PID controller. So implemented using the active components, for example, the op-amp as active network. This PD controller means what exactly? The sum of the differentiator and a pure gain, also called an ideal derivative compensator. Its purpose is to improve the transient response of the system. So what exactly the PD refers to this PI controller, as it is the sum of the integrator and a pure gain. Also it is called an ideal integrator or integral compensator, and its purpose is to reduce the steady state error to zero. And hence, the purpose of PID controller is to improve both the transient response and steady state response, that is zero steady state response. See this figure, one PID controller is shown. So its transfer function is given by Gc of S or G of S is equals to K1 plus K2 by S plus K3 by S, and that is equals to, we get in numerator K1 of S plus K2 plus K3 of S square upon S, and by solving simply very easy to solve, as we discussed how to reduce this block in very first unit. Okay, that is block reduction technique. Apply this technique, so we get in numerator K3 outside as it is common, and take inside the bracket S square plus K1 by K3S plus K2 by K3S upon S, which has the 2 0 plus a pole at the origin and 1 0 and 1 the pole at the origin, and can be designed as the ideal integrator compensator. The other 0 can be designed as the ideal derivative compensator. While improving both the steady state response and transient response, both can be improved independently. For an approach, we can improve the steady state error first and then follow with the design to improve the transient response. A disadvantage of this approach is that the improvement in the transient response in some cases yields some decay in the improvement of the steady state error, which was designed first. In the other case, the improvement in transient response yield further improvement in steady state error. Thus, a system can be oversigned with respect to steady state error. So, this oversight is usually not a problem unless it affects the cost or produces the other design problem. Here, I am going to design a controller for improving the transient response first and then design for reducing the steady state error. First, the PD controller, that is proportional derivative controller, has to be designed to improve the transient response. And then we have to design the PI controller to obtain the required steady state error. Now we are moving towards design of PID controller. So some steps are generally used to design the PID controller. I'm discussing this step one by one. Evaluate, first thing is that to evaluate the performance of the uncompensated system to determine how much improvement in the transient response is required. Second, design the PD controller to meet the transient response specification. The design includes the zero location and the loop gain. Third, simulate the system to be sure all requirements have been made. And next, redesign if the simulation shows the requirements have not been made. The next, design the PI controller to yield the required steady state error. Next, determine the gain K1, K2 and K3, and it is shown in first figure. Now simulate the system to be sure all requirements have been made, and at last redesign if the simulation shows that the requirement have not been made. So this PID controller design example is taken here, and that example belongs to uncompensated feedback control system. So the given system is a design to a PID controller so that the system can operate with a peak time that is two birds or two-thirds that the uncompensated system at 20% overshoot and with zero steady state error for the step input. See this diagram? Now searching for the 20% overshoot in the figure, we find the domain poles at minus 5.41 plus minus 0.6j and with a gain of 121, and corresponding damping ratio is sigma is equals to 0.456. Now the step response of the uncompensated system with the gain value of 1 to 1 is shown in figure. See this diagram? It is found or it shows the result when the overshoot is 20%. Now when the value of k is 121, then it should be the step response of the uncompensated system. The peak time is observed as 0.3. Okay. Second, we know that the dominant poles are given by the roots sigma omega n plus j omega d, where this omega d is equals to omega n under root of 1 minus sigma square. And now the peak time, that is Tp, is given by Tp is equals to pi upon omega d, and that is equals to pi upon 10.6, and it is equals to 0.2964 seconds. So the next step, a PD controller has to be designed to reduce the peak time to two-thirds of that of the uncompensated system, that is 2 by 3 into 0.3 seconds, that is equals to 0.2 seconds, and its theoretical value is 0.1976 seconds. So the dominant poles for this desired peak time of 0.1976 seconds can be obtained by theoretical means. And from the peak time relation, the imaginary part of the desired domain pole omega d is obtained as omega d is equals to pi upon 0.1976 and its value is 15.9. Now, for finding the real part of the desired dominant pole, a line has to be drawn to the left of the imaginary axis in only S plane with respect to the origin at an angle. Theta is equals to cos inverse of sigma, and cos inverse of sigma, that is C, value of sigma is 0.456. So the value of this theta will be 62.87 degree as shown in the figure 6. See this diagram. So it is shown here clearly. It is a right angle triangle formed in S plane to find the dominant pole. So what is the value of this tan? So tan of 62.87 is equals to 15.9 upon sigma omega n. And when you calculate by using scientific calculator, you get the value equals to 8.147. Therefore, the dominant pole for the desired transient response specification of a peak time 0.1976 seconds are minus 8.147 plus minus 15.9 J. Now we start the design of PD controller by finding the location of the controller design 0 using the root locus property as shown in figure. See this figure. By connecting the dominant pole to the all uncompensated poles and zeros. Here see the four. Here the angle formed between the dominant pole and all other poles and zeros can be obtained as follows. See here, four values of the theta are given, that is theta 1, theta 2, theta 3 and theta 4. So theta 1 is equals to 107.94 degree, theta 2 is equals to 97.69 degree and theta 3 is equals to 90.53 degree. So depending upon these three values of the theta, that is theta 1, theta 2 and theta 3, we find out the tan theta 4 and it is equals to theta 4 83.35. Now the angle of contribution required from the PD controller 0 in order to make the root locus to pass through the desired dominant pole can be easily obtained. So angle of contribution is equals to 180 degree minus sum of the angle from the dominant pole to the 0 . So angle of contribution is equals to 180 minus sum of the angle from the dominant pole to all other poles plus sum of the angle from the dominant pole to all other zeros. So from this we can easily find out the angle of contribution is equals to 180 minus in first bracket theta 1 plus theta 2 plus theta 4 plus theta 3 is equals to minus 18.45 degree. So using this geometry, we can easily find out the value of tan of theta and from which the location of the PD compensator 0, that is Z0, is found to be minus 55.8. Therefore, the transfer function of the design PD controller is given by GPD of S is equal to K into S plus 55.8. Now, the loop gain of K equals to K for PD compensator system can be determined by either manual calculation or from the root locus graph of the PD compensated system. and it can be determined by either manual calculation or from a root locus graph of the PD compensator system. The complete root locus of this PD compensator system JPD of S into G of S is shown in the figure. Please take this diagram. From the root locus, this graph obtained from the MATLAB simulation, and it is evident that the dominant pole for the PD compensation system with 20% overshoot shows minus 8.17 plus minus 5.9 J with the loop gain of 5.39. Now we can check the loop gain value through manual calculations. Now see here this determination of loop gain K for PD compensator system. We know that the location of a dominant pole is a closed loop pole location, and the closed loop pole can be obtained directly from the characteristic equation for various values of K. Here we know that the dominant pole has minus 8.147 plus minus 15.9 J, and corresponding K value can be obtained as follows. So the characteristics equation for a system is given by 1 plus G of H of S is equals to 0, and since the given system is unity feedback system, that is H of S is equals to 1. Therefore, the characteristic equation is simply 1 plus G of S is equals to 0. This transfer function G of S of the PD compensated system, including the loop gain K, is given by a particular equation, that is G of S is equals to K into S plus 8, S plus 55.8, S plus 3, S plus 6, S plus 10 in denominator side. So now we have to check the PD compensator design with the loop gain of 5.39 in MATLAB simulation. This step response of PD compensation system is shown in the figure, and the peak time is observed as 0.174 seconds with the loop gain value of 5.39, and thus it is evident from the simulation that the PD compensated system satisfies the peak time required better than the desired one and operating with the overshoot of nearly 22%. At first, very first time, it is the overshoot of 20%. Means here the gain of 2% overshoot will be happens, and the result is satisfactory. The comparison of step response of uncompensated system and PD compensator system is shown here. See this diagram. So from this figure, it is evident that the uncompensated system has a steady state error of 1 minus 0.843, and PD compensator system has 0.07, and thus the PD compensator system having the improvement in steady state error also. Even though this PD compensated system reduces the steady state error over the uncompensated system, and the given requirement is zero steady state error. So we need to design the ideal integral compensator to reduce the steady state error to zero for a step input. Any ideal integral compensator 0 will work as long as the 0 is placed close to the margin origin. Here I am choosing the ideal integral compensator 0 to be 0.1, and thus the transfer function of PI controller is given by GPI of S is equals to S plus 0.1 upon S. Now the loop gain K for the PID compensated system can be determined by either manual calculations or from root locus graph of the PID compensated system. The complete root locus of the PID compensated system is shown in this figure, and from the root locus graph obtained from the MATLAB simulation, it is evident that the dominant pole for PID compensated system with 20% overshoot shown with a loop gain of 5.32. Thank you.